Let me know if you can see the screen. Okay, so yeah, first notion is convergence in probability, right? So here we are discussing the convergence of random variables. So sequence of random variables, say converging to some other random variable x. So xn is a sequence, um, right? So we say that they converge in probability if if this sequence converges. Sorry, yeah, this sequence converges. Okay. Um, what does this say? Given any epsilon, okay, however close to zero, but greater than zero. Um, this difference, right, the xn minus x, should eventually go to zero in probability. That is important. Okay. Here, the sequence under consideration is the probabilities, not the sequence themselves, but the sequence of probabilities, right? So, yeah, just to be elaborate that, here we define, say, Pn to be this event. Okay, this event is probability that xn minus x greater than epsilon, right? Now, if you see, this Pn defines sequence for every n, every n, right? Now, what we are actually talking about when you say that something is converging probability is this Pn goes to zero. Okay, not the xn minus x goes to zero. This Pn is going to zero. Okay, so what does it mean for any sequence to going to zero? This is the definition of convergence of sequence. Pick any delta that is positive, then you should be able to find a number n delta, right? I mean, this n can vary when you change delta, such that whenever n is more than n delta, your Pn is guaranteed to be less than delta. That means a sequence converges to a limit. In this case, it is converging to zero. You give me any however small number close to zero, I can find an n such that whenever after beyond that point, all the numbers in Pn are less than that delta. Right. So that is the convergence of sequence. So actually the question of what is converging in convergence of probability in converging in probability is this Pns, not the xns. Okay, so that is convergence in probability. Any questions on this? I mean, I try to be as clear as possible, but yeah. Are there any questions on this? We assume Pn converges to zero in advance while proving it. Yes, that's true. That's true. Because Pn has to converge to zero by definition, right? This is the definition, right? This is the definition. The limit, it has a limit. If it has a limit zero, only then we say it is converging in probability. Okay. So yeah, so what is one instance of this convergence of probability? You can say it's an example or application, not an application, but example. Ignore this word application. Okay, so it's weak law of large numbers. So xi, let xi's be IID random variables, each with mean mu and variance sigma square. I mean, we don't use variance explicitly, but any finite variance is fine. Then your average of those random variables converges to mu, which is the true mean in probability. Okay, so what we have to show here? We have to show this sequence, right? We are talking about this sequence. Okay, this sequence should converge to 0 in the limit. Right, so simple Chebyshev inequality, right, on this random variable x minus, if you see expectation of this Sn by n is mu, right? Crossing epsilon is 1 over epsilon square by variance of this thing, right? That is by Chebyshev inequality. What is variance of Sn over n? It is 1 over n square times variance of Sn, because xi's are IID. This is nothing but n times variance of xi, which is assumed to be sigma square. Okay, all xi's have same distribution because of IID assumption. Right? This is nothing but sigma square by n. Now take the limits here. So you have proved this by Chebyshev inequality. Take the limits. What is happening here is, in the limit, this term is going to 0, and probabilities, and this probability in limit is less than or equal to 0. You know, probabilities are between 0 and 1, right? So that's it. So that's why it has to go to 0. That's the proof of weak law of large numbers. I am assuming this is clear. Right? We'll go to the almost sure conversion. Okay, cool. Now this is the difficult part of the entire whatever we'll be discussing today. Okay. So what does the statement here? Right. You have sequence of random variables xn's, and they are converging to some x. Okay. So this is a statement. We say an almost sure convergence if this holds. So notice the difference from the convergence in probability to almost sure convergence. They're telling entirely different things. Here, since xn's are random variables, right? It's a function of your sample space, right? Pick any point small omega belong to your sample space, and now you analyze how each random variable is behaving at that omega, right? Now fix an omega and scan all the xn's. Now for each omega, xn of omega is a sequence, is a normal sequence of real numbers, right? For every omega, this xn of omega should converge to x of omega for every omega, right? And you collect all such omegas, and if you evaluate the probability, that should be 1. So actually what it is saying is, the set of all omegas that satisfy this property is nothing but your sample space, right? Because probability on the entire sample space is 1, right? So this is, you try to understand the difference between this almost sheer convergence and convergence probability. Here we are saying these PNs are converging. Here we are saying that xn is converging to x for every possible point. Okay, so entire sample space should converge, right? And some fine notion to this is, uh, a set of omegas can allow to diverge, right? They need not converge to x of omega if the probability on that omega is 0. You don't care. Basically, wherever probability is 0, you don't care about what happens. Okay, so that's why it is almost sure, not everywhere. But by saying almost sure, you are only concerned on the points where there is non-zero probability assigned. Clear what I meant by almost sure convergence and convergence in probability. Do we take limits in this definition? Yeah. So when I'm saying the sequence xn is converging to x, it is in the limit. So after omega, it should be limit here. Ideally speaking, there should be a limit here. This omega such that limit n tends to infinity, xn of omega tends to x of omega. So wherever I write this arrow, it is in limiting sense. Okay, and mind you, limit is not before this guy, before the probability. Limit is inside this probability here. Okay, so I have written the same thing, whatever I just explained here. Okay, now we want to characterize this thing further, right? Um, so that's what, right? Fix omega and now evaluate each xn at that omega for every n. Then this sequence has to converge to x of omega in limit. Okay, so by definition of what is the convergence of sequence, what is the definition of convergence of sequences? You give me any epsilon positive, I'll find a capital N, which is a function of epsilon, right? Such that the difference between my converging point, which is capital X of omega, and the sequence xn of omega is guaranteed to be less than epsilon when my small n is greater than this n epsilon, right? So it's like a game. You can think of convergence of sequences. Someone gives you an epsilon, right? You should be able to find an capital N such that whenever your N is more than this capital N, you are guaranteed to be within that epsilon from your target. Okay, is it clear? Cool. So yeah, let's try to be a bit more precise. We can put epsilon is anything, and so let's take epsilon as 1 over k, where k is an integer, right? So then we simply change the definition to for all epsilon greater than 0, we put for all k greater than 0. Okay, now there exists an nk such that for all n greater than nk, you are guaranteed to be less than xn of omega minus x of omega by 1 over k. Basically replacing epsilon by 1 over k. That's it. Yeah. Okay. One more thing. Here, xn's are functions. Okay. And frankly speaking, this capital N can be different for different omega. Which Archimedean property? Uh, we are not exactly referring to Archimedean property here. Basically, what Archimedean property says is if you have any real number, say x and y, right? So you can find an n such that your n times x is more than y, right? Or any real number, you can find a natural number more than x, right? Yeah, you can say that, yeah, Archimedean property. You can find the k more than such that you can make it less than epsilon. But yeah, that is not our intent for putting k here, as you see. Okay. Mm, yeah. So what does this mean? Right. What does this mean? The forget PR probability here. Just analyze this set. Okay. So for every k, right? For every k, for every means an intersection. Okay. So there exists an nk, right? There exists as a union. Okay. Again, for every n greater than nk, right? Nk. I mean, just ignore this greater than or equal to or greater than. There can be some minor typos. That's not important. Yes. So we want to have this condition satisfied, right? Right. And for every omega, you want to satisfy this condition, right? For every omega, right? And if you evaluate probability on this entire omega, that should be 1. Okay, so this is important. It's clear, right, how you got from this point to this point. Yeah, so basically they are coming uh, from the definition of the convergence of sequence. So you should be able to satisfy this thing, right, for every k, right, for every k, for every k, and you are evaluating at every omega. Every omega, basically all omegas, set of omegas that satisfies this thing, right? For every k, you want this condition to be hold true. That's why it is intersection over case. And for every k, given a k, you're saying there exists an nk. So there exists, whenever this you have a phrase there exists, it means a union. Means it can lie in say nk, it can lie in nk plus one, it can be lie in nk plus two, right? And once you fix an nk, you are saying again for every small n more than nk, this should hold. Again, whenever you see every, right, it should hold for all n's which is more than this nk. Okay. So mm, frankly speaking, this nk should be a function of omega. Okay, so we'll get rid of that. We'll see how we get rid of that. Now you see this condition should hold true for every k, right? Because it is intersection, right? And what I mean by that is, if k is equal to one, you put k is equal to one, and you see what are the set of the points belonging to this, right? Again, you put k is equal to two. Again, you check the set of points belonging to that, right? Ultimately, all the points that satisfies this should be such that when you evaluate your probability, it should be one, right? Because it holds true for every k, we can just fix a k or given an any epsilon, right? Just fix a k. Even then, it should satisfy this, right? They're just fixing a k. Again, you're going back to epsilon. Okay. Right. So now this is what we have. We'll take a complement of this to get into a more familiar notion. Just take a complement. One will become zero and unions will become intersections, and the events will also flip. Flip in the sense, here you have less than epsilon, here you have greater than or equal to epsilon. Okay, that's it. So now, I hope this is clear. This is simple only. We're just taking complement of this event. And let's define some ANs here as this, how much you're deviating xn of omega minus x of omega greater than or equal to epsilon. Should have written a epsilon of n, but that's fine, right? So this is a familiar notion. of intersection of n union n greater than n an. We just called this as this one as an. That's it. Okay, and you have this intersection n union small n greater than n. We call this as limit superior. So if you see this ans, uh, uh, if your random variables are defined on, say, on a probability space omega fp, and ans are the sequence of events in f, right? And you know that unions, arbitrary union of ans belong to f. Again, the intersection of any number of events also belong to f, right? So this is a valid event. You can assign probability to that, right? There's just a side thing I'm just telling that, yeah. So this is an event and it has a non-zero probability. I mean, it can be zero, but yeah, it is a valid event. Okay, so what we want is finally you have reduced to this, the complicated looking thing, this thing, right? You have reduced it to this. You just want limit superior of the sequence of events an to be zero, probability of that events, right? Uh, what is an is how much you are differing from the target random variable given an epsilon, right? So yeah, that's it. That this is where we are now. From, right, this is how you characterize a convergence of strong law. You can characterize directly from definition, or like this, right? Why I'm saying like this, as you know. So here we have a couple of things. One is Borel-Cantelli lemma, right, which allows you to decide when this event is zero or one. Okay, so whenever this is zero, you can say that, right, this thing holds, right? Almost shear convergence holds, right? Because we have derived that by the definition of almost shear convergence, we have derived this. Okay, if it is clear till now, we can go to Borel-Cantelli. Hmm. We are not taking link soup. It is by consequence of this thing, right? This is this equation clear? These two are clear, right? Yeah, we're getting, by taking complement of the above one, you got this, whatever is highlighted. Now you're defining an to be this event. Okay, that's it. Once you define an, the entire this thing, whatever is there in this argument, we are calling that is by definition is a limit superior. That's it. We are not taking limit superior. It has come by the arguing from the definition of the sequence, convergence of sequences, right? We ended up here. Finally, we see that maximum deviation becomes zero. That's true. Okay. Yeah. So now, if we want to evaluate this event, when you can say this is zero and when you cannot say this is zero, right? Evaluating limit superior is a bit difficult in the sense it involves intersections and unions, right? So there's a Borel-Cantor lemma offers a easy way to when we can say that limit superior is 0 or 1. Okay. If the sequence P of an is less than infinity, summation, right? You view this as a series now, right? P of an sigma n is equal to 1 to infinity. That series, if it is finite, then limit superior is 0, right? Okay. So let's see what is this. Yeah, that's what we are proving it now. Okay. Now what is limit superior of sequence of elements, right? It is by definition, it is this n is equal to 1 to infinity union of n is equal to n to infinity an, right? So this is what is the probability of lim sup is this, right? So let's see what this looks like. Put n is equal to 1. Okay, if n is equal to 1, this lower, inner union is a1 union, so on, an. Now fix n is equal to 2. And we call this as b1, right? All this union, you call it as b1. Put n is equal to 2 at b2. Define b2 as a2 union, a3 union, so on. N is equal to 3, b3 is a3 union, so on. Right? You notice that this b1 is containing b2, b2 contains b3, and so on. These are the sequence of decreasing sets, right? And what actually you want this thing, this intersection n is equal to 1 to infinity union n is equal to n to infinity is this, right? Intersection of BAs, right? And just notice that B1 contains B2, B2 contains B3, and so on. And by monotone limit theorems, you know that probability of limit n tends to infinity, right? Intersection of this decreasing sequence of events is nothing but your limit n tends to infinity probability of Bn, right? Because fix any Bn, that Bn is nothing but intersection of 1 to n Bi. I mean, we have proved this in the early initial classes, initial sessions. Okay. Um, that's it. Okay, so in our case, what is Bn, right? In our case, this Bn is nothing but we just map it, right? Bn is this quantity is Bn. Okay, so that's it. So probability of intersection is n is equal to 1 to infinity. Bn is nothing but your limit n tends to infinity probability of Bn. Okay. This is clear. Is this clear so far? Clear, right? Okay, so now we are defining uh, this event. Um, this thing, right? Bn. What is Bn? Bn is the union of A's starting from capital N. Okay. So from this step to this step, it's a union bound. Okay. Probability of union of AI is less than sum of A's. Probability of A's. Okay. Now, if you see this thing, and So probability of an sigma 1, and when n goes from 1 to infinity, that's the entire sum. And this sum is called as tail sum as n goes to infinity, right? Because the sequence, because they are what I've written here, right? This is the tail sum of this entire series. And you know this series convergence, right? The series converges to some finite number. When it can converge to a finite number? Only when the tail sum goes to 0, right? Right. Clear? Are the arguments clear? Why this sum should go to 0? Need not be, right? And just 10th term going to 0 is not good enough. You can say take sigma 1 over n, right? A harmonic series. That nth term can go to 0, but then tail sum still goes to infinity. So you need the entire, yeah, you need the entire series to converge, right? Because the entire series is converging to some finite number, right? The tail sum should go to 0. It has no option number to go to 0. So you can just take um, the geometric series 1 by 2 plus 1 by 4 and so on, right? And so say that is sigma 1 by 2 power k. Now, if you sum till infinity, you get 1, right? Let's say, but you sum to 1000, right? You get a number very close to 1, but not 1. The tail sum is becoming smaller and smaller as you increase the n, this n, right? So that's why we say the tail sum eventually goes to 0 in the limit. That's it. So limits are important here. Nothing is precise. Only in the limiting sense they happen. Okay, so now we have proved that probability of lim sup is 0 if if this condition satisfies. Right? We have proved the first part of this theorem. Right? So there is second part to it. Okay. Now what this says is if your series diverges, series of probability of ans diverges, right, and ans are independent, right? The independent assumption is important for part 2. Then you say that limit superior is 1. Okay. Oh, let's prove it. Just take the definition of limit superior. I mean this thing, right? Again, define B capital N as this thing, union of n greater than or equal to n again, right? And you want to prove this is 1, right? Same as earlier, just take the complements. Intersections becomes unions and events become complements of events. Bn is B complement and this is 0. Right? You prove this if you prove this to be 0. Okay. Again, notice that by the way we defined Bn's, right? This guys form a increasing sequence, okay, of events, right? Again, use that limit continuity theorem, right? With this thing, probability of union of n is equal to 1 to infinity is same as n tends to infinity probability of Bn complement, okay? Right, Bn, just substitute whatever is Bn complement here, like this, okay? And because of independence, you are able to factorize this as a product. This is where independence assumption is used, right? Here, this step to this step, right? Again, yeah. So this is the same thing I have written here. Use the inequality 1 minus x is less than e power minus x, right? You get e power minus this thing, right? And what is given to us? Uh, this is pi, right? So this will end up as the summation, right? We are given that probability of an diverges, right? So if the series diverges, then the tail sums can never converge. Tail sums also have to diverge, right? And that's it. If this goes to infinity, this goes to zero. This limit in the limit it goes to zero, right? And that's it. So we have proved that. What we have proved? We have proved this thing, right? If if this series diverges and ans are independent, limit superior of an is 1. Okay. Clear. So one application of Borel-Cantor lemma is strong law of large numbers. We will see the proof of this now. Okay. Cool. So what does strong law says? So this average xn by n, xn's are IID, right? Not in probability, almost surely, or with probability 1, it converges to the mean, right? Each x's are IID random variables with mean mu, and we also assume one more thing, it has fourth moment. To be precise, it should be fourth central moment, but yeah, its fourth moment exists, right? So what do we have to prove? Since we know that Borel-Cantor lemma, right? We have to prove if an is defined like this, right? The deviation from its mean, right? And if once you define an like this, then if you show that probability, I mean, to show that probability limits of an is equal to 1 is same as showing that Sn by n tends to mu, right? As we have discussed earlier under the strong almost sure convergence, right? So what do we want to prove? We want to prove that sigma probability of an is finite, right? Once you prove probability of an sigma n is finite, then by Borel-Cantor lemma you can say that this holds. Right? If this holds, you have proved that Sn by n converges to mu almost surely. Clear? Okay, so what is by Borel-Cantor lemma? We need to show that this thing is less than infinity. Just take what happens if you take Chebyshev inequality. Right, this is what you get, right? Variance of this sigma square over n, right? Now, if you sum this left right side thing, this is harmonic series 1 over n. It diverges. Okay, it will never converge. It always diverges. 1 over n. So we don't need so that Chebyshev inequality is of no use. So that's why we assume we have access to fourth moment. Right? The same thing is less than or equal to this thing, right? Right. This is coming by Markov inequality, right? I mean, when power is 2, you call it as Chebyshev, but otherwise, in general, it's a Markov inequality. Right? We want to see what this term evaluates to, right? Sn by n minus mu whole power 4. So we want this thing. This is nothing but 1 over n power 4 expectation of Sn minus n mu whole power 4. Right? Now Sn minus n mu is what? Since Sn is sigma xi, right? Substitute sigma xi here, you get sigma of xi minus mu whole power 4. Okay. This power 4 is contains sigma. But just for convenience, let's define zi is xi minus mu, right? And variance is sigma square and mean is 0. Mean of z is 0, right? So what is this thing? Now we want to evaluate this thing, right? Sigma is equal to 1 to n, zi whole power 4 is nothing but sigma ijkl, right? Zi zj, zk, zl. I just expanded sigma, that's it. Notice what terms remain and what terms vanish here. All the terms of the form I not equal to j not equal to k not equal to l vanishes because zi's are id and e of z is 0. And any term that contains cube term and another term, right, that also vanishes because of independence, and e of zj is 0, right? This term vanishes. This term vanishes. Only remaining terms are this, right? Whenever I is equal to j is equal to k is equal to l, and other terms like x1 square, x2 square, x3 square, x4 square, and so on. So there are 6 possibilities in which those terms can happen, right? So once you take expectation, right, you get because there are only I, j, k, l goes from 1 to n. You have n here, and you have 6 possibilities in which you can have e of zi square, e of zj square, right? You are summing up from I and I greater than j. Basically, I not equal to j, just sum it. And what else? Yeah. So basically, what we want is we want. I mean, exact uh, count here is not of importance. What we want is we want an upper bound that varies more than 1 over n. Right. That exponent we want to be more than 1 over n per 1. That's it. Right. Here you have n times e of z per 4 plus 6 times, because e of zi square is sigma square, e of zj square is sigma square, you have sigma per 4. And when you sum this two, right, even if you assume that you have taken everything, right, you have counted more than whatever it is, right, it cannot be more than n square because this sum runs from 1 to n, this sum runs from 1 to n. Okay. So we can say I've written as O of n square. I mean, that is less than some k times n square, right? It's not important, but what is important is it is n square. It is not more than n square. That's it. Okay. So what does this thing evaluates to? Right. The entire thing is by n power 4, you have this thing, right? Just substitute that, and what you will get is we'll get two terms. One is k1 k prime by n cube plus k2 prime by n square. All you want is this kind of thing, right? Now summation of this converges. Why? Because you know this, say sigma 1 n square 1 over n square converges to pi square by 6. I mean, if sigma 1 over n square converges, sigma 1 over n cube should definitely converge, right? Because each term is lower than 1 over n square. In general, any series with 1 over n power p converges whenever p is more than 1, right? Okay, so what you have proved here is correct. All the terms are of the order of n square. Yes, yes. In this summation, they cannot be more than n square. because it is sum over two indices I and j, and each is going from 1 to n. Okay. Yeah, so basically, uh, once you have this as a function of some k times n square, right? I just repeated this thing divided by n power 4 because we want this, right? Um, right. So after when you divide by n power 4, what you get is you have a term of n and you have another term of n square here, right? A term of n will give you n cube in denominator and k2 prime some constant, which is a function of your sigma square, and some constant from this O term, right? And that is also divided by n square because it cannot be n cube for sure, because even if you count the worst case, right, all possible ij, even I here exact sum is I greater than j. Even if you count everything, right, it is at max n square. That's it. Some constant times n square. That's why I've written O of n square. So finally, it is this. Right now, this will converge. This will converge. Right now, if this converges, right, this will also converge. The sigma, the sum of n is equal to 1 to infinity, sigma n is equal to 1 to infinity converges. So by Borel-Cantelli lemma, right, you have shown that what we have shown is you have shown that this sigma probability of an is less than infinity. This guarantees by Borel-Cantelli lemma lim sup of an is 0, right? But what is lim sup of an? When lim sup of an, when an is defined like this is 0 means Sn by n converges to mu with probability 1. Is it clear? Yeah, I mean, you have to work on this to get better clarity. Yeah, I mean, listening to this can be bit difficult at first go. I mean, I try to be as clear as possible, but yeah. Is it clear? I mean, what we wanted to prove, the bigger picture clear. Forget about this minor details here. So the bigger picture is we want to show that the sigma xn by n go to 1, right? So for that, we know that if we show that probability of lim sup is 1, then we are done. When an is defined like this. When we can have this thing, the Borel-Cantelli lemma, probability of sigma an to be less than infinity, right? If that is less than infinity, we know that this by that Borel-Cantelli lemma guarantees we have this thing, right? Now to have this, we tried Chebyshev inequality. We have got a denominator of order n, and if we sum this, it will be infinity, right? We cannot conclude anything that this sum left side sum also be finite. Okay. To get a higher order more than n per 1, so we have tried to bound it tighter by taking fourth moment, right? When you take fourth moment, you ended up terms in the denominator greater than 1, that is namely n cube and n square, and we know that this converges to a finite value. That's it. So that's how you show that. I mean, if this is converging to finite, sum should also converge to finite, right? Once you show that p of an is less than infinity by Borel-Cantelli lemma, this converges to 1. Sn by n converges to mu with probability 1. Okay. Yeah, I mean, these are difficult things, but yeah, you have to see whatever I have written, see in the internet, see for any other YouTube resources which can give better explanation, right? But I hope I made clear the distinction between almost sure probability and the convergence in probability and their immediate theorems: weak law of large numbers, strong law of large numbers, and the Borel-Cantor. Okay, so convergence of mean, there's nothing much to talk about. If when you say convergence in mean is zero, if this limit goes to zero, expectation of mod xn minus x per r goes to zero in the limit. That's it. So if you just have apply Chebyshev inequality, right, convergence in second mean, tooth mean, when your r is 2, implies convergence in probability. That is again by Weak law. I mean, check this. You can try to prove this. Should be able to prove this for any random variables. To try this. If not, we can do it in the second coming week. Right? Convergence in mean implies convergence in probability. Okay. So finally, the last form of okay. The last form of convergence is convergence in distribution. Right. So we say sequence of random variables xn converges to some random variable x in distribution of the following holds. Fn's are sequence of distributions of xn's of random variables xn's. If fn converges to f, right? Fn's are distribution functions and it converges to f. And if f is a distribution function of some random variable x, then we say xn converges to x in distribution. Right? It's a sequence, it's a convergence of sequence of functions. Right? A function under question is distribution function. Okay, so that's the definition of convergence in distribution. And yeah, now we'll come to central limit theorem. Now here we want to show that when Zn is defined like this, right? Think, yeah, there's no sigma here. That's a typo. Sn by sigma times root n, right? Where is Sn? What is Sn? Sn is the summation of random variables xi. Zero mean IID random variables, right? With variance sigma square. So all it's saying is Sn by sigma root n converges to standard normal. Right? Xn's are any ID, Sn is the sum of IID random variables. Right? We're not assuming any distribution among themselves. All we are assuming here is independence and IID, identical distributed. Okay, how do we prove this? So we don't show the distribution function converges. Instead, we show the characteristic function converges. Okay. So what we want to show is this Zn, characteristic function of that Zn converges to e power minus mu square by 2. Right? If characteristic function converges, then the distributions also converge. Okay, so we only show that characteristic function converges. And this e power minus mu square by 2 is the distribution function, is the characteristic function of standard normal. Okay. And yeah, just what is phi x of u is by definition, it is expectation of this thing, right? And we do a Taylor series expansion of this thing, of this phi x of u around 0. And this is the Taylor series expansion, okay? And phi x of 0 is 1 and phi x prime of 0 is 0 because of 0 mean assumption, right? If you take phi x prime of u, you get at 0, you get expectation of jx, and that is 0. And phi x double derivative evaluated at 0 is minus sigma square. You should try to do this, try to show this. It's very simple, right? and just substitute these things back, you get this thing. Okay. And finally, what we want is expectation of this quantity, the characteristic function of Zn, right? Just substitute that thing here, and Sn is nothing but sigma xi, right? And just because of this exponential having summation in the argument, you is the product. Because of independence, you are able to take expectation inside that. Okay. That's all. So this is nothing but because of IID assumption, each of this evaluates to same quantity, and this you get whole power n, right? And you know that phi x of u is this thing, right? And you evaluated u, but u here is not u. You have to evaluate it u by sigma times square root of n, right? This is changed. Earlier you just have u, right? Here you just have to substitute u by sigma square root of n instead of u, right? So when you substitute, you end up getting like this: e1 minus u square by 2n plus o of u square over sigma square n whole bar n, right? In the limit, when you take this, you will get the final desired quantity. I mean, this is not trivial to prove this to this, but yeah, this limits a value is to e power minus u square by 2. Then show that. Is it clear? This is this just algebra out here. There is nothing different we have done. Okay. Maybe you can just look at the steps once I upload this PDF, or you can look anywhere elsewhere also. Okay, so some problems, right? So we have consider polling of n voters and record the fraction Sn of those polled in favor of a particular candidate. If P is the fraction of the voter population, right, that supports a candidate, then Sn is the fraction, the way you are defining is sigma xi, I is equal to 1 to n, where each xi is Bernoulli random variable, right, takes 1 or 0. Okay, so how many voters must be sampled so that your estimate is within 0.02 of P with probability at least 0.9? So what they are asking is, so there's a fraction of voters P that favors a certain candidate. Okay, and you want to empirically evaluate that. That P you don't know, but you want to empirically evaluate that. And what you want is you want very high confidence that your evaluation should be close to the true value P. I mean, it should not be more than right 0.02, right? It should be less than 0.02, right? And that confidence has to be at least 0.9. Okay. So, Hofding, there is something called as Hofding inequality, right? So this probability of 1 over n sigma is equal to 1 to n xi minus e of x. That is being more than epsilon is upper bounded by this quantity 2 exp of minus 2m epsilon square by b minus a whole square, where each random variable xi lies between a and b with probability 1. Okay. So what these guys want is here epsilon they have given as 0.02. Okay. So just take the complement of the problem. What we want to do is, they want at least 0.9 probability, right? The confidence. So at most with 0.1 probability, we will break this rule, right? I mean, we can deviate from P with at most 0.1 probability. That's what this sentence means, right? The probability under the question is this quantity, okay? This guy. Okay, this guy should be at most 0.1. And this can be at most 0.1 if you make this quantity at most 0.1. Okay. Okay, what we are given is 1 minus delta, that is 0.9, and delta is 0.1. You just substitute 0.1 here and evaluate it, and you end up getting, you need at least this much samples to be uh, close to the true value uh, with this much tolerance, 0.02, and with this much confidence, 0.9. So this is Hopding inequality. I mean, probably next time I will try to prove this, right? So I'm just taking this as an formula as of now, but yeah, one can prove this. Improve it next time. Is it clear? Okay, and some easy problems finally. X1, X2, X3 are random variables, and Xn is geometric random variable with parameter lambda by n. That is P, right? So what is n? Yn, we want distribution of Yn is Xn by n, right? We want just take Yn probability Yn greater than alpha. That is nothing but probability Xn greater than n alpha, right? This probability is nothing but sigma n alpha plus 1 to infinity q per k minus 1 times p. Why? Because Xn is geometric, right? Basically, geometric distribution takes value k with the probability q per k minus 1 into p. So it is the waiting time to get a success. If p is the probability of the event which you call as success, it's the waiting time. And that's the definition of geometric random variable. Just evaluate it, right? You end up getting this like this, right? This is nothing but exp of minus lambda times alpha in the limit. Okay? This is a straightforward calculation. How you got this thing is q is nothing but 1 minus p. What we are given is p, lambda by n. Right? Evaluate the sum. This is nothing but p times q power n alpha, and this is 1 by 1 minus q. Pp goes, and q per n alpha. Q is 1 minus lambda by n alpha in the limit n tends to infinity for e. This is exp of minus lambda. Okay. I think that should be fine. So another use of Borel-Cantor dilemma. Right, Xn is normal distribution, zero mean with 1 over n variance. Sigma square is 1 over n. Okay, and what we want is to show that it converges to 0 almost surely, right? So what does we want to show? If you define this as an, and you want to show that sigma of this probability of an should be finite. Okay, let's define this probability of sigma and probability of mod xn greater than epsilon is upper bounded by e of xn per 4 by 6 epsilon per 4 actually. It's a typo here. And for Gaussian, you know that e of x per 4 is 3 times sigma per 4. Okay, and sigma square is 1 over n, right? And substitute that. For our case, sigma square is 1 by n by definition. The problem. And this is nothing but some constant times 1 by n square. You know sigma 1 by n square converges to a finite value. So does this left side, right? And by Borel-Cantor lemma, this converges to 0 almost sure. Okay, is it clear? Okay, finally, the last one is the almost sure convergence thing. S is uniform probability, uniformly distributed, and right, that is, I mean, the way you define is the probability measure of between A to B, between A and B is nothing but B minus A. I mean, that's just a definition of uniform distribution. And you have sequence of random variables xn of S as n by n plus 1 times S plus 1 minus S whole power n. Then xn converges almost surely to S. Okay, let's see how. Now, this can be solved. You need not go for Borel-Cantor lemma and all, right? You just pick some S, okay, and see how, as you keep varying in, how where does this go? Fix an S. In the limit n tends to infinity, this n by n plus 1 goes to 1, right? And because S is between 0 and 1, right? 1 power something less than 1 to the power of infinity goes to 0 always, right? So in this way, xn of S n tends to infinity goes to S for all S, right? So this is what we wanted, right? For all S, and you measure the probability of all S, that is 0 to 1, that is given by 1 minus 0, that is 1. So the probability of this is 1. That's why it is converges to S almost surely. Okay. It's clear. Recording stopping.